quite a low spectral flux. And the standard spectral features, there are also kind of other features from statistics, like spectral cortices, skewness, and so on. Now, let's move on to perceptual domain features. Well, we are going to focus on a few handcrafted perceptual domain features from tempo, pitch, loudness, and critical band representations like the famous MFCC, commonly used in speech recognition and the news information retrieval, and finally, chroma vectors. So, about the tempo. Can anybody tell me what is the tempo? We have musicians here, right? How do you perceive tempo? Okay, clearly that is the definition here. Tempo in music reference refers to the speed at which a piece is performed. But that is quite abstract. Let's actually have an example. So, in this case, given a piece of music, how can we automatically identify the beats? If we can do that, and it's relatively easy to determine the tempo, am I right? So, we human beings can easily perceive the musical beat here. But given we have a time domain signal here, how do you compute the beat automatically? That is the beat detection problem. Very interesting. And I have done some research by myself as well. There are a lot of papers published in this domain. And why is beat tracking a hard problem? Is this beat hard to track for you guys? No, it's very easy, right? But what's the problem with the computers? Beats sound different in different songs. There are a lot of diversity here.
Galveston, oh Galveston, I still hear your sea winds blowing.
Okay, so beats are not necessarily constant within the same song. Do you agree that the tempo changed dramatically in the middle? And other sound can obscure the beat. So with so many sounds mixing together, it is not very easy to determine the true beats there. And the sound beat can be blended with other sounds. Okay, the tempo can change. So regarding the beat tracking fundamental algorithms, we have the time domain signal like this. We can compute the action signal. Basically is the process of feature extraction. Then we compute the periodicity and then identify the beat location. That is the typical process. How do we do the beat detection? Okay. About the tempo. I hope that is a reasonable introduction. Any questions so far? Good. Let's move on to another very important perceptual domain feature called pitch. We talked about frequency last week. Then what is the difference between frequency and pitch? Especially we are talking about a fundamental frequency, correct? So if we have a music notes, remember how does the music notes look like in frequency domain? We have the fundamental frequency, and then we have also harmonics, correct? But what is the difference between the fundamental frequency and the pitch? Can anybody distinguish these two? How many of you, by the way, attended Dr. Emmanuel Beneto's tutorial? Okay, do you guys still remember and Jonathan and Joe? So what is the difference? He clearly explained this difference between fundamental frequency and the pitch.
Pitch is perceptual.
Yes, correct. That is a very key word here. I like to hear that. So I hope that this is already clear enough that I can remove this, right? Okay, very nice.
The different combinations of harmonics can actually give you the same pitch.
I'm sorry?
Different combinations of harmonics
Uh-huh.
can give you the same pitch.
Okay. So I give you an example here. If we have a harmonic structure looks like this, for example, a piano notes, right? Here is FO, and here is 2 times FO, 3 times FO, and so on, correct? So then basically, this guy here is the fundamental frequency. Typically, is identical to the pitch as well. But the difference here is that if we remove this guy here, fundamental frequency, can we still perceive the pitch? Correct. So therefore, pitch here is a perceptual attribute. But a fundamental frequency, although it's related, but it is not identical. With these remaining harmonics, we can perfectly perceive the pitch for human beings. Is that clear? So I just wanted to distinguish these physical attributes and perceptual attributes. Okay? Raise your hand if there is any confusions here. Okay? Then, to define the pitch, people invented, I think it's Professor Alan Chu, invented this kind of representation. The pitch can be represented like a spiral curve here. Basically, the pitch can jump into octaves, like A4, A5, A6, and things like that. So although it sounds the same, is it correct to say that it's the same pitch? Probably not. Right? It's octaves. The pitch jumps in octaves. Okay. Then, how do we determine the pitch? What are the harmonic sounds? So in time domain, a harmonic sound could look like this. We can even compute the what is it? So the frequency based on the time domain features. And then we could do this also based on the frequency representation here. So basically, these gaps between these spikes here represent the fundamental frequency, and then also the lag between these spikes here, and then 1 over F1 is the fundamental frequency, and we can also compute the pitch here. Okay. There are many kind of audio samples that we can observe. We plotted some of this waveform of a widening sound in time and frequency domain. As you can see, the pitch, the widening sound could be very periodic. This another one is the cymbal crash in the time and frequency domain that is very much noise-like. Pitch basics, that even the pitched percussion of plucked instrument are semi-harmonic, and then we also rely on the harmonic to determine FO. It's quite harder to determine the pitch from instruments that are not harmonic, of course. What else could be difficult to determine pitch? Particularly for our musicians. Typically, music signals is not monotonic. Rather, we have a lot of components mixed together, right? Even for piano, you can actually hit multiple keys in the same time. With violin, can you actually produce multiple pitch as well? And how many pitch you can produce? Up to 4 in the same time. Okay, right. In this kind of situation, multi-pitch detection until today is still a challenging research problem. It's not very easy to determine this detect the multi-pitch if they are mixed together. And then, as I said, so the pitch computed in the time domain, there is a famous algorithm that we are going to cover in one of the future tutorials. It's called in algorithms. But anyway, the idea is relatively simple. We compute autocorrelation from the time domain signal and then try to determine the legs between these peaks here. So using this one, the legs, to determine the pitch. So in this particular case, assuming that we compute this autocorrelation function here, and then we find out the peaks of the first the peaks in this autocorrelation function. Let's say the leg is 170 samples. Then we can use this leg to compute this pitch. Oh, it's roughly 259.4 hertz is the note C4. Since we are going to cover these in algorithms in detail later on, I'm probably going to skip these parts. Okay. This is about the pitch, and then how do we compute pitch? Any questions so far? All right. Then now let's talk about the loudness. Again, we have some problems here to play back these samples I produced here. The loudness is again a perceptual attribute, how loud we perceive the sound. And correspondingly in its physical attribute is the amplitude of the sound. Assuming that we are talking about just a sinusoid signal. What I tried to produce here is to produce exactly the same the sinusoidal tone with exactly the same amplitude, but in different frequency range, from 50 hertz to, let's say, 8,000 hertz. Remember, when we generated the sinusoidal tone, we only need 3 parameters here, right? Amplitude, frequency, and a phase. We keep here the phase to 0, and the amplitude is exactly the same. We only change the frequency. I tell you the condition. You can generate this by yourself. Ideally, do this experiment. You use headphone in a very quiet environment. Using this loudspeaker anyway is not a very good idea to do this kind of experiment. So can you imagine? I generate this sinusoidal tone across the frequency range. Are they going to sound equally loud? Yes.
No, because higher notes sound louder, like naturally.
I'm sorry.
Like, do higher frequencies jump out at you more when you listen to them? So if you only change the frequency, the loudness isn't going to be the same.
It's not going to be. This conclusion is absolutely correct. Assuming that we change the frequency from 50 hertz, that is actually the power supply frequency there, and then to, let's say, 20 kilohertz. That is almost the upper limit for most human beings, okay, with exactly the same magnitude. So you guys can easily do this by yourself, generate this sinusoidal tone with the 3 parameters here, and then listen to that, and how that will sound like. So do you think, okay, let's say, according to the psychology study and the psychoacoustic study, human beings are particularly sensitive to sound around 2 to 3 kilohertz. Meaning you can almost imagine for the sinusoidal tone towards 20 kilohertz, right? Although the magnitude is exactly the same, but many people hear nothing. Meaning the loudness is 0. Can I say that? But the same signal around 2 kilohertz to 3 kilohertz, these sound very loud. So you can almost imagine this curve looks like this. Does it make sense to everybody? So anyway, and if you are interested in that, and unfortunately this computer has not installed the correct audio codec, I cannot actually play back these samples. But that is the observation that you could easily observe. And by doing a simple experiment by yourself, okay, generate this number of sinusoid and then listen to this sample by yourself. Okay? Oh, also, I generated one with a just piano kind of notes with the fundamental frequency present and removed the fundamental frequency. Basically, the pitch does not change at all if you remove the fundamental frequency. I just wanted to kind of illustrate in this particular case what is the difference between the physical attribute and the perceptual attribute. Okay, this is the so-called equal loudness control. As you can see, by the way, how do we interpret this curve like this? Here, this is the frequency domain representation in the logarithmic scale. Here is 100 hertz. Here is towards the 20 kilohertz. What does this curve mean in this particular case? So-called equal loudness control. Meaning, if we want to generate a sinusoid which sounds equally loud, if the frequency is as low as 50 hertz here, I need a very intense sinusoid to generate the same loudness sensation. But if we put this frequency around 2 kilohertz, we need a very, very low amplitude there. And that looks like this. And as I said, the experiment I want you guys to do is just exactly the opposite. So we keep the physical amplitude of the frequency constant. Then this loudness looks like this, correct? But here, if we want to keep the perceptual loudness the same, then the physical amplitude must be very much higher here, very much higher here. That's, in fact, the interpretation of this equal loudness control. Is that clear? Any question? All right. Anyway, this can be computed as well.
I have a question.
Yes.
So,
Huh?
in the unit decibel, what exact feature does it measure?
I'm sorry?
What feature does decibel, like the unit of loudness, what's that? Like it's the perceived loudness, right?
The intensity level in decibel. Intensity, that is the physical attribute.
Yeah.
Meaning, I could probably right here. Let's say y xt. Oh, so let's see. The signal could be a let's say y or I'm sorry. Still confused. A sign. So let's say just we are talking about a sinusoidal tone here. So we have three parameters here: amplitude, frequency, and phase, right? So here, this intensity meaning, we are only considering these guys here, the amplitude here. That is the intensity. So this decibel value here, you probably know how to compute the decibel value, right? This is a log value. So basically, we are computing this log A times 20. This becomes the decibel value. And with this one here, 6 decibels here, you can imagine how much it will change in terms of the intensity here. Does it make sense?
Yeah, I think I understand.
Okay, very nice. Any other questions? Okay, then the loudness is okay now. Then, now let's move on to another very important handcrafted feature called MFCC. Okay. Well, this one is also try to mimic the human capability, how we perceive the sound. I wanted to kind of remind you guys about this human inner ear. Remember, this is the cochlea, and as I said, this the basilar membrane is about 32 millimeters in long. Assuming this, if we cut this thing to 1 millimeters in length, from the low frequency to high frequency, in fact, the human ear is much more sensitive when the frequency is low. When the frequency is higher, let's say the frequency value of 10 kilohertz and then 20 kilohertz, all will actually vibrate toward the very end. But in the lower frequency range, we have a much higher resolution there. So therefore, the bandwidth in our ear is not equally distributed. That's also a fundamental difference between FFT or DFT and the human auditory system. So that doesn't make sense to you? So when we try to mimic these human auditory systems, in fact, these bandwidth will change and non-linearly. And that is the computation we are talking about here. So we compute the FFT being this dark signal here is the DFT spectrum. spectrum. So how do we compute these to reflect the human perception then? So we will try to compute these differently. Okay. In the first case, we divided this number of filters to 4, meaning we have this kind of shape, and we multiply these f of t coefficients with the window shape, and then add all these values together. We will form one single value for this first band. Second band, we do the same thing, multiply the spectrum with this window shape, and then have just one value out. We have the second coefficient. Third, like this. Then actually these f of t beams, let's say in this case we have 250 values. After this single operation, we have just 4 values out. Is that clear? That this is actually a very rough kind of operation, try to mimic what human auditory system does. And then we can do the same thing, and when the number increases to 10 to 20. And then what we get in the first instance, we have just 1, 2, 3, 4 coefficients here. And the same thing here, and we are going to have 10 coefficients here. Roughly, you can still see that it follows the FD contours there. Okay? And then when we increase this to 30, this looks like this. It actually still looks to mimic the contours of the f of t spectrum. So we try to map the frequency domain representation to the perceptual domain. But remember, this bandwidth of human auditory system is not linearly distributed. That is a very important message here. Okay? Remember, that's actually what I'm trying to remind you guys. So this is the cochlea here, and with the basilar membrane rounded like this. When the frequency is 100 Hertz, it vibrates here. One is, for example, 10 kilohertz is vibrates here. But from here to here, that's a huge range. But the vibration always happens here. Is that clear to everybody? So meaning our inner ear has a much finer frequency resolution towards the lower frequency, but much worse frequency resolution towards the high frequency range. That is what I tried to say. And we try to mimic this capability using the concept of critical bandwidth filtering, meaning here is my f of t coefficients in the frequency domain. But please remember, here is the critical step to map the frequency domain representation to perceptual domain. Perceptual domain, because this bandwidth is going to increase like this non-linearly. We have to somehow combine the frequency domain representation to the perceptual domain representation. Using the method, we try to mimic this like this. We combine the energy within that particular bandwidth to one single value there. And then the only thing is that with this, we are going to do this combination like this. The bandwidth, you can see, if we use the single triangle bandwidth to kind of mimic the human auditory filtering, so this triangle is very much sharper. And here, this triangle is much kind of broader. That's the idea here. Is that clear? Very good. Any questions so far? That is the idea of the critical bandwidth concept, and what this MFCC is trying to mimic. Okay. So that is the male frequency capsule coefficients, how this thing is computed. So our next assignment is going to something about MFCC computation,
Yes,
right?
like how to write a program to compute MFCC.
Excellent. So here I just wanted to tell you the steps. How do we compute this MFCC? The idea is already conveyed in the previous slide. But here is our audio signal. We processed it frame-wise. We cut in a short frame here. We do the winnowing and the pre-emphasis. And as you can see, the signal after this windowing function looks like this. Okay? And then we perform a FFT and compute the magnitude of the spectrum. It looks like this. Correct? Then we do this mapping like this. Remember, this step, everything is quite mechanical and linear. But after this step, we map this representation from the frequency domain representation to perceptual domain. Is that clear? So that's why this nonlinear representation starts from here. After this, we perform a log operation and then perform a DCT, and with truncation, we are going to get a feature like this. That is so-called feature. For every frame of audio sound, we are going to get a vector like this. That is the steps to compute the MFCC we are going to exercise. Of course, you can call from some library to compute this, but in reality, how do you compute this? You need to know how to do that by yourself. So is that clear, or whether there is any questions here? Yes.
What does the MFCC vector tell us?
What does this tell us? And this is a rough estimation how we human beings perceive this sound. That is the coefficient that tells us. But of course, that is a very rough estimation. For example, can anybody tell me, after we combine this energy within this critical bandwidth, why do we want to perform a lock representation here, lock operation here? Can anybody tell me? Remember, for the pitch, right? We're talking about the piano keys. So the frequency is not increasing linearly, but is in a logarithmic scale. Is basically one octave after another. And the loudness, and we try to kind of mimic here, is also in a logarithmic scale. So the loudness is not increasing linearly, but logarithmically. Yeah, things like this. Anyway, that is a convenient feature very commonly used in speech recognition. So that is the log frequency equation that you can do to do this mapping, and then according to these functions here. Afterwards, in this particular case, we are going to have 120, for example, dimension of vectors. Okay. So that is something like concrete examples how we compute these feature vector. And then this one will show you what really happens to map the time domain signal to frequency domain, and then how do we use this MFCC feature to compute these feature vectors here. After this step, every frame, what we get is just a vector here. It's called features. That is, again, to emphasize that if we kind of visualize the vibration of this basilar membrane. So cut this into 1 millimeter in length. In fact, in lower frequency, it is much denser and much finer representation. But towards the higher frequency, even this remember this 100 to 200, the difference is only 100 hertz, right? But from 10 kilohertz to 20 kilohertz, is actually the duration is almost 10 kilohertz in length. But all these vibration happens towards the end. And that's also something that I explained. When you lose this high frequency kind of perception, in fact, this high frequency component you cannot perceive anymore after this part is damaged. Okay. These are some mathematical functions to mimic the critical bandwidth. Remember, this is the center frequency of these triangles, or the different kind of shape of the filter bank changed from low frequency to high frequency. And if towards the low frequency, the bandwidth is roughly how many? And below 100 hertz. But towards the high end is as wide as 10 kilohertz in bandwidth length. Okay. These are some functions try to mimic these auditory systems filters using this gamma tone filter bank to model the critical bandwidth. Remember, that is the fundamental difference between this representation and the Fourier analysis. Because Fourier analysis, when we have a linear time domain samples in, we are going to have a linear representation in the frequency domain. But in reality, what happens in our ear is different. Okay, and let's move on to the final perceptual domain feature that we discussed today is about a chromatic vector. How do you compute this? And that is very much a music related features. So I just prepared just one slide here. Maybe I could try to use this whiteboard to show what really happens. Assuming this is the frequency, hertz, this is the amplitude. Okay, let's say this is the the spectrum of one piano notes. How do you compute this chroma vector? Assuming this is hertz. What is this note? I'm sorry? Is the A. Right. But if this is the A notes, if we jump one octave higher, is 880 hertz, right? So typically, this thing and this thing are all very much related, right? If we combine all these harmonic component, the energy together, we will get one vector, one value here. Okay? Then, what is the B frequency? You understand? Yeah. So A is 404 hertz. But what is the frequency of the B notes?
get like that.
Okay, but anyway, it's not necessarily a integer number there, right? But according to this formula, you can compute. So all the piano notes in the between an octave, how many keys do you have? 12, right? This is called a semitone. So basically, then for all these, and then you combine this energy together, and then all together, every notes can be combined to a vector of 12 numbers. You just combine the harmonic energy together. But of course, there are different kind of ways to compute this value. But the point is that with this simple kind of transform, you manage to transform every notes to a 12 domain vectors, regardless of how many, how long your analysis will exercise. So this is actually the procedure that we try to illustrate here. So we have the audio data with no overlapping windows, perform f of t, you get a representation like this, then collapse that to 1 octave, so to 12 pitch classes, and an average magnitude of these beams, we got this chroma vector. This vector is very much used in music information retrieval research domains. But do you think that this chroma vector is going to be useful for other sound processing like speech? Why not? Correct, yes. So that's why this feature is designed specifically for music signals. Okay. So that's all the perceptual domain features that I plan to talk about. That is the summary of today's lecture. We have a recap of the key concepts learned so far. We introduced to several important perceptual domain features. And finally, I wanted to say something about career advice for the new century. I use this, my own experience, as an example to show some important ideas here. Of course, music has always played a very important role in my life. This is a place and the career trajectory that I personally experienced. Okay. I'm originally from China. It's a small village near Shanghai, and then spent 15 years in Europe, worked for a company called Nokia, and then moved to Singapore and worked in the US for 16 years. And I spent 2 sabbaticals in North America, including 5 months in Boston and 3 months in Toronto. What I wanted to say is that my life trajectory actually almost resembles a shape of birds and freedom in academics. So I like this analogy here. And this is actually the advice I got from my teachers in my home university. And that translated into English is something like this. Education is not only about reading books, not only about getting good marks, but actually education, especially university education, should be much broader. That's why I definitely encourage you to travel more, to explore the world. Remember the last sentence that I said in my first lecture, right? So it's a learning journey to explore not only the outside world, also to yourself. And then also make friends in many countries and disciplines and succeed in having a positive impact in mankind. So building bridges is important. That's why, and I will encourage you guys to also download this S-Lines app and then have a critical review of that. So that is a student project. We are going to continue this project. I'm actually recruiting new students to continue this project. And this is a question that I somehow invented by myself, called 3I, convolution with 3H equals to 3P. What does this I mean? I think for our students, I very much emphasize these 3 I's. First of all, intellect. I believe everybody sitting in this classroom are definitely, all of you are intelligent. But this second I is imagination. That is important too. It's not just kind of remember things that is not going to bring you very far. Imagination is an important attribute. The third I is initiative. Do not just kind of follow instructions. You need to take initiative to think beyond what we taught in class, for example. Then this 3H is we try to kind of foster this kind of environment so that you are healthy, happy, and hardworking. This will lead to educate you to become a better person, to publish more papers, and create a patent and a useful product for society. So that is the equation supposed about. And then another important question to promote kind of debate or discussions is about, are musicians smarter? What do you guys think? How many of you actually are amateur musicians? Can you please raise your hand? Don't be shy, please. Raise your hand. All right. So what's your view? So are musicians smarter? This is a question that we discussed during my sabbatical in Boston. What do you think?
Yes.
Yes. So what's your justification to say yes?
I don't have a justification, but
I'm sorry?
I don't know. I mean, they're smart. That's what.
They are smart. Okay. As simple as that. Okay. We have quite a number of musicians here. But the point is that, okay, smartness maybe is not from the genetic level. The point is that our brain, of course, we inherited something from our parents, but the actual use of the brain will generate more connections in the neurons in your brain. The music practice somehow serves this purpose. That's why many people argue that musicians are smarter. And some people even try to kind of have some scientific evidence. But the point is that, okay, when you use your brain more, and you will probably get smarter. And that's also one interesting topic when I visited Stanford for the first time, and they had this music and a brain symposium, and cultivated a lot of discussions about this and how we can use music actually to help people in terms of health, in terms of learning. Okay. Anyway, that is a cycle that I also kind of borrowed from my collaborators in neuroscience. Everything starts from the brain. We use the brain to control every part of our body, our hands, our feet, and our mouth. And then we can use these to generate music. And then the music can get back to our ear, to our eyes, to our skin, and then back to the brain. This forms a very nice circle. So ear is an important organ in this function. So that's actually the lecture for today. Any questions? Okay. If not, we can take a break and wait for lunch. Nick?